először Charles introduce Camelia Pop from the University of Switzerland and Untitled Chapter.
Thank you very much for having me here. I will speak about Harnack inequalities for degenerate diffusions. And from the title, you can see that it should be something that is connected with partial differential equations. We will have some solutions for which we want to prove a Harnack inequality, but at the same time it's going to be related to some degenerate diffusions. And this work is going to be Charles Epstein. The degenerate diffusions that we are going to consider, the one-dimensional version, is what we call the Wright-Fisher process. And this is a process that originated from studying certain quantities that arise in population genetics. And it's a one-dimensional process that is actually well understood. But I want to start with that process just to explain what is the intuition about the process. And then we're going to move to the multidimensional generalizations, which we're going to call Himura processes. And then related to these Himura processes, we would have an operator and some solutions to a PDE for which we're going to prove Harnack inequality. And the proof of the Harnack inequality is probabilistic, so it will connect somehow with these processes that we have here. So the motivation, as I said, comes from population genetics, where people want to understand the evolution of a genome in a population. So for example, imagine that we have a chromosome, and on that chromosome we fix a locus where a gene can form, and that gene can have different versions that we call alleles. And for simplicity, let's just assume that we have two alleles, capital A and little a. And we want to study how frequent does each of these alleles occur. For example, this allele can model a trait in a population, for example, of mice. Some of the mice can have yellow fur or brown fur, and we want to understand what is the proportion of the mice with yellow fur, what is the proportion of the mice with brown fur. And this is going to correspond to the frequency of allele capital A, respectively the frequency of allele little a. So we will look at the process x of t, which is the frequency of the gene capital A at time t. And then in this two-dimensional model, so just two alleles, 1 minus x of t is going to be the frequency of gene little a. And it's enough for us to understand x of t. And this process should be random, because even though we can see today what is the frequency of the yellow and the brown mice, we cannot know tomorrow what that is. It's going to be a random variable for which we would want to understand what is the distribution. Now, this process x of t, it is easier to understand it as a discrete process, like a discrete Markov chain. It is easier to specify it in that way, but maybe not as easy to understand it analytically. So people have taken continuous limits of this discrete process. So for us, x of t is going to be a continuous limit of a discrete Markov chain. And we still call it the Wright-Fisher process after the biologists who first introduced it in the 20s and 30s. And these continuous limits have been studied by people as Kolmogorov, Feller, Kimura, and also people like Freya, Bass, Barlow, and Perkins. These authors have studied these processes in connection with different applications, not to gene frequencies. But it's the same kind of a process. Now, before I say exactly how to specify this process, I want us to just look at some questions that are of interest, that we want to understand about the processes. So, in this picture, the gene frequency is on the x-axis, and it's going to take values in between 0 and 1, because it is the probability that that gene occurs in the genome. And this is the time axis, the way the gene frequency evolves in time. Now, the gene frequency can evolve following different paths, right? Because it's going to be a random process for us. And we want to know, well, if the gene frequency is X today, what is the probability that at time t, the gene frequency is Y? And this is the transition probability. It's going to be a function of time, of X, the initial gene frequency, and Y, the gene frequency at time t. Now, for the Wright-Fisher process, we will see that we can write down formulas for these transition probabilities. But for the multidimensional processes, we won't be able to write down formulas, but we want to understand what is the regularity of these transition probabilities, and most importantly, what are the singularities of the transition probabilities. So for example, think about the heat kernel. A heat kernel, it is like the transition probability for the Brownian motion, and for the heat kernel, we do have a closed form formula, and we can see what is the regularity, what are the singularities. It is something similar that we want to do for these transition probabilities.
You have P of Tx and dy.
So in general, this is going to be a distribution, right, on the interval 0, 1. And we will see, so in the following slides, I will show some formulas for how this transition distribution looks like. In general, it is a measure. That measure may have a density with respect to the Lebesgue measure, may have some delta functions, some singular measures. So in general, we just write it ptx dy. So that is the probability that if I start at time 0 from x, at time t, I am in a very small neighborhood of 1.
But there's no explicit dependence on y.
So dependency on y, I just
that's a differential form.
dy. Yeah. So these are some of the things about the transition probabilities. What can happen is that we can also have a stationary distribution. So if this process is in a stationary distribution, it means that at subsequent times it keeps the same distribution. That means that genome is not going to evolve anymore. And do these stationary distribution exist? If they do, we just want to understand them. Also, what can happen is that some of the alleles are fixated into the genome or are lost. So, for example, a trait can be lost. And we want to understand what is the probability that that loss occurs. And maybe also at what rate does that loss occur. And that has to do to understanding the spectral theory for an elliptic operator that I will show next.
So does that last part presume that there is a stationary limit, and then you want to see how rapidly you approach that limit?
Yes, if it does exist, yeah, because it's not obvious that it should exist, yeah.
Can it ever be periodic?
This one, yeah, no, I would say no, yeah, because it's a diffusion. Diffusions, you should think about them as time irreversible, so they don't have a periodic behavior. So I want to write down a model for the Wright-Fisher. And this model, so the gene frequency X, is going to solve a stochastic differential equation. So just to understand this stochastic differential equation, ignore for a moment this vector that is multiplied against dw. W is going to be a Brownian motion. So if I ignore the vector, what I have is that a small increment in x equals to some coefficient times a small increment in time. This is actually just an OD, and I can solve this, and if I do that, I will get a deterministic path. And of course, that is not a good model for a gene frequency, because tomorrow I cannot tell what the distribution of the genes are. I need to add some randomness into this model. The way randomness is added is through this dW term. So dW is a normal distributed random variable that has mean 0 and variance dt. So to a small increment of the gene frequency, I will add something deterministic through this drift, and also something random because I'm adding a small normally distributed random variable, which is through this dWg, and it has some coefficient. Now this form of the coefficient is not random, it has a biological interpretation. It comes from the way we are taking the limit from the discrete process to get this continuous process. And I'm not going to explain that limit, I just want to explain a few things about how does this process behave. So x of t is supposed to be a gene frequency, so it's supposed to only take values in the interval 0, 1. And it's interesting what happens when and if the process hits the boundary point 0 and 1. So let's assume what happens at the 0. I see that because of this x of t, this red coefficient is going to be 0. So that means that at 0, we are killing the randomness into this model. If I'm also assuming that this beta 0 is 0, then this term is 0, x of t is 0, so the whole blue coefficient is also 0. So I have no more drift, so dx of t is 0. There is no more evolution in the process. The process will be absorbed at 0.
Why do you put the square root?
That has to do with the limit from the discrete process. Yeah, which I'm skipping now. Yeah. So, but what about if this beta 0 is positive? Let's see what happens at 0. If beta 0 is positive, then this drift sums up to beta 0. So the beta 0 pushes the process back inside of the domain. So now, even though we are killing the randomness, there is a drift that pushes the process back inside of the domain, so it's no longer absorbed at 0. This beta 0, it actually has to do with the mutation rates of the frequency process. Because at 0, that frequency disappeared from the genome, but because of mutation, it can appear again, and that's modeled through this drift.
If the ecosystem conditions are changing in time, wouldn't you want these beta 0 and beta 1 to depend on t?
Yeah, so they can depend on time, but here I'm showing a more simplified model. Yeah, but in the end they can depend on time. Yeah. So now I want us just to look a little bit at the transition probabilities. The way I can understand those is as solutions to the backward or the forward Kolmogorov equation. So this is our SDE. Now the backward Kolmogorov equation is going to be, I'm assuming here that B has a density, so it is going to be a function of time x and y. At time 0, it is a function, so y is fixed, it is a function of time and of x. X is the backward variable. So at time 0, we will just assume, because the transition probability started from y, at time 0, this is just a delta measured at y. When time becomes positive, we take a derivative in time equals to an operator that only acts on the x variables. So we have the second derivative in x multiplied by 1/2 the square of the red coefficient, of the coefficient of the Brownian motion, the randomness, plus the first derivative in x times the coefficient of dt, the deterministic part. And it's important, this operator on the right-hand side. This operator, we call it the infinitesimal generator of the process, because if we understand that operator, and if we can solve, let's say, this backward Kolmogorov equation, then we get these transition probabilities. And once we have the transition probabilities, we can use them to actually construct a solution to this SD. So this operator actually characterizes the process. I want to say a few more things about the Wright-Fisher process, and I will consider separately that case when the process is absorbed and when it is not absorbed when it hits the boundary. So again, here when we are assuming the mutation rates are 0. So we have only randomness and we have no drift when we are hitting the boundary, so the process will be absorbed at 0 and at 1. And I said that for the Wright-Fisher process, the transition probabilities are understood. And it has the following structure. So the transition probability will have a delta measure at 0 because of the absorption, a delta measure at 1, again absorption at the boundary point 1, and something that is absolutely continuous with respect to the Lebesgue measure. Now, these delta measures have coefficients that this psi 0 is exactly the probability of absorption at 0. The psi 1, the coefficient of delta 1, is the probability of absorption at 1. And this other density, PD, usually we call it a Dirichlet heat kernel, but that actually describes the distribution of the paths that are not absorbed up to time t. And here we can take the limit when t goes to infinity, and these transition probabilities will converge to the stationary distributions, which are the delta measures at 1 and at 0. And it's intuitive because if we start at 0, we kill the randomness, there is no drift, we stay at 0. It's a stationary distribution. Now what happens when we do have
So you're
mutation?
saying classical analysts would understand the transition probabilities, and you're putting a path process behind it, so to speak,
Exactly.
behind this analysis.
Yes,
Right.
yes, exactly. And now I want us to look to the process with mutation rates. Now what happens when the process hits the boundary? Because of the mutation, it is instantaneously reflected back inside of the domain. And now the transition probabilities, they will just have a density which is absolutely continuous with respect to the Lebesgue measure. There are no delta measures now because there is no absorption, intuitively speaking. This density is smooth inside of the domain, and it has singularities at the boundary points. And those singularities, they look like y to the 2 beta 0 minus 1. So these singularities are power-like singularities, and what power? The power is determined by the strength of the drift coefficient, of the mutation rates. So the mutation rates play a very important role in understanding the transition probabilities, and that is expected. In this case also, we can take a limit, so this PTXY has a closed form formula. We can take a limit when t goes to infinity, and we find a stationary distribution, and we find in this case that we have a beta distribution. And the parameters of the beta distribution actually imagine a beta function with parameters 2 beta 0, 2 beta 1. So it's totally different, not delta measures, but something that has a density. We will want to do similar things for the multidimensional diffusions, but it won't be as obvious to do. So what we will do is to study the parabolic problem, just like in the backward Kolmogorov equation. Because that's the equation that determines the transition probabilities, and if we can understand it well, we can hope to get information about the transition probabilities. And I will say more about how we can do that. So let's assume that I want to solve this problem. The derivative in time equals to the operator L applied to a solution U. But now my initial data is a function f, which is not anymore a delta function like for the transition probabilities, but I choose to be something smooth. And I want to understand what kind of solutions can I get to this parabolic equation and what are the regularity properties. And okay, first of all, I can use the transition probabilities that I had before to construct a solution. I just take the initial data and integrate it against the transition probabilities. What I find is that this function that I put over here solves the parabolic problem, and it is also a smooth function up to the boundary when x goes to 0 and when x goes to 1. And also because it's smooth, is the unique smooth solution. There is a maximum principle that applies to this operator, and we get uniqueness. But if you look, so I should say, before I talk about uniqueness, I want to point out the fact that when an analyst would write this formula for a solution to the parabolic equation, a probabilist would write this formula as an expectation of the initial data composed to the frequency process x of t. And this is exactly the same thing because the distribution of x of t is given by this kernel. But I want to point out this because this kind of expectation is something that we call a stochastic representation. For this problem, it's easy to get, but in the following slides, we will see a more complicated problem for which the whole issue is going to be to get the stochastic representation. So to keep in mind that whenever we solve this kind of parabolic problems, we can hope to represent the solutions into the form as an expectation, as an average of the initial data composed to some underlying process, the gene frequency process in this case.
And that integral is y, the variable of integration?
Yeah.
And why isn't the dy outside the parenthesis?
It's just notation. E of tx, y, dy is a measure.
For example, it can be a delta measure, so I just put it inside. But you should imagine a measure. Yeah, so that's a measure, and it has a distribution in y.
Should say y.
And just a few comments about uniqueness. So in this parabolic problem, we had an initial data, but I didn't say anything about the boundary, the boundary condition on the parabolic part of the boundary. So on these red vertical lines. And there are no boundary conditions. So without any boundary conditions, uniqueness holds for these solutions in the classical smooth functions. And the reason why that is true is because there is a maximum principle. And when you have a maximum principle, it is straightforward to get uniqueness. And hopefully more than that. So now we have extension. We are going to look at multidimensional extension of the Wright-Fisher process. These multidimensional extensions, if we want to study the transition probabilities, we won't have closed-form formulas like we had before. And one of the reasons why we won't have closed-form formulas is because the operator that arrives in these extensions is not going to be self-adjoint. So for the one-dimensional case, that operator L that I showed before, it is self-adjoint with respect to a weighted L2 space. We will lose this kind of property. But still, we would want to solve the parabolic problem and understand the regularity of solutions that we get to that parabolic problem.
The self-adjoint depends on the function space that you need. You're saying no function space exists that makes it self-adjoint?
I think this is the natural function space.
No, for this one, but for the higher dimensional,
yeah,
it doesn't exist?
Yeah, I mean, I don't know any natural choice.
Okay.
So that's, yeah.
Does this problem also have a biological motivation?
It does have a biology. Yeah, so the multidimensional extensions,
Mm-hmm. Yeah.
they do. So what I showed before is like you have only two values, right? And then I showed that picture that you have mice that can have a fur yellow or brown. But, the color of the fur is in a whole spectrum, and that actually means that you have a multi-dimensional number of values. Yeah, so it's very important to be able to understand the multi-dimensional case. So, and this multi-dimensional generalization, we call them Himura processes because Kimura was a biologist who proved many good things about them. The way I'm going to write them, I will use the formulation of Janet and Great Mazzero. So Kimura was not as general as in what I'm going to show next. So these are generalized Kimura diffusions. And just like I said before, these processes or similar processes have been studied with application with different application to super processes in particular. And the authors that I can reference here is Freya, Bass, Barlow, and Francis. And this multidimensional generalization will have a generator, and that generator, so an operator, just like L, and that operator L will preserve the key properties of the generator of the Wright-Fisher process. Also, these multidimensional processes will live on a simplex. So let me just say a few things about these simplexes. In general, they will live on a compact manifold with corners, but by that I will just imagine a simplex. So when we will write the operator, we will write it in local coordinates, and we only need to study that operator at boundary points. So I just want to point out some local coordinates at boundary points. So for example, in this corner, my local coordinates, I can think about these two axes, and the neighborhood, I can write it as the interval 0, 1 squared. Both coordinates have to stay positive at this corner. If I look at this other boundary point, then again, these are the axes that I will choose, and I see that only one axis is restricted to stay positive, and the other axis, on the other axis, the coordinates can take any real value. There is no restriction. So a neighborhood here is the interval 0, 1 times minus 1, 1. So now if I'm in multi-dimensions, a neighborhood will be some copies of the interval 0, 1 times some copies of the interval minus 1, 1. So those are part of this space S and M, which are n copies of the positive real line times n copies of the real line. And in this space, the infinitesimal generator will take this form. So I should start with this point Z. In S and M, I will write the coordinates x and y. The coordinates x have to stay positive. The y coordinates can take any real value. So if I look, these are the terms that are highlighted, and they are the most important. The rest, we can think about them as perturbations. So if I look at the second order derivative in x, these are multiplied by some nice coefficients a, I, but also by xi. And the xi goes to 0 as we are approaching the boundary of this domain S and M. Now, because of this degeneracy, the strength of the second order coefficient decreases as we are approaching the boundary. And the first order derivative will start playing an important role. The mutation rates will be important as we are approaching the boundary. So this is the reason why I highlighted this first order coefficient. And the way we should think about this bi, that it is a drift or a vector field that either it's 0 on the boundary or no, that tangential to the boundary, like an absorption, or is pointing inside of the domain, and that makes the process to be reflected back inside of the domain. And then in the y-coordinates, the y-coordinates are nice. The y-coordinates is like a Laplacian. Of course, we can make the coefficient variable. So I add some variable coefficient happened when I studied this operator.
Is it always a fixed sign? The DLK?
DLK, so it will be a matrix, and I'm thinking about that matrix as being symmetric, positive, definite, and the smallest eigenvalue is bounded from below by something positive. That's why I say that it's like a Laplacian.
And in the corner, what do you know about the AIs?
AII, think about them again as being positive and bounded from below by something positive. Yeah. So if I would be removing the xi's, I would have something nice, like a Laplacian. But I do have the x. Yeah. So the features of this operator is that it is not strictly elliptic because of the xi's that go to 0. And they go to 0 in a precise way, linearly proportional to the distance to the boundary. So if I have something going to 0 exactly like the distance to the boundary, it makes this second order term like a first order term in the scaling, the way it scales. So again, the sign of the BI is going to be important, and as I said before, we always assume they are non-negative. So we can either allow absorption or reflection back inside of the domain. And from a fitting point of view, when we study the regularity of solutions, the boundary of the domain SNM is important. And we see that the boundary is not smooth, it can have corners and edges. And for example, if I would study the Laplacian operator on this domain, I cannot hope to get solutions that are smooth up to the boundary. They will always have singularities. But that is not the case here. So let me say the result that we already know, and then I will say what we do to add to this result. So the result is due to Harnack and Matzel. Imagine that we are on a complex manifold explorer, so on a simplex. And I want to solve this parabolic problem, and I have an initial data f and a source function g. And I'm assuming that the initial data f, it is Holder continuous. The source function g, it is also Holder continuous, and these are Holder spaces that are designed precisely for this operator. Then the result says that I can get a unique solution to the parabolic problem that again is Holder continuous in a proper Holder space. So this is Schauder theory for this operator. And it's practically the theory that we know for the Laplace operator, but the Holder spaces are modified such that they are suitable for something with this kind of degeneracy. And I will say a little bit about how they are modified. They also get an a priori estimate. So in that a priori estimate is basically how can we control the regularity of solution in terms of regularity of the data. And it says that the higher order regularity of the solution U is controlled in terms of the Holder regularity on the source function G. And here I highlighted the Holder regularity of the initial data. So in order to get this kind of regularity, what I want to point out in this result that the initial data has to be Holder continuous. And then we gain more regularity.
But you need the boundary data.
We
You don't
have-
gain on the boundary.
No. Yes, so this regularity falls up to the boundary, up to the parabolic boundary. And we only have an initial condition. No, yeah. And I want to say a little bit about the Holder spaces. So we call them anisotropic in the sense that the distance function with respect to which we define these Holder spaces is not the usual Euclidean distance function like for the Laplace operator, and is given. So we consider this fundamental form. So we view it as a manifold, Riemannian manifold, such that written with respect to the new distance function, the operator containing the second order coefficient looks like a regular Laplacian. So what you see in this distance, that the way we're measuring the distance in the degenerate direction, the xi's, is practically the absolute value between the square roots of the xi's. That's the only thing that changes. To the Holder spaces, there is another modification in terms of the second order derivatives, but I won't say that because it's not going to play a role in what I'm going to show next. Just to keep in mind that this is and this distance function it's normal, it's natural to associate it with the regularity of solutions.
If you change the
You said that the distance is equivalent.
It's equivalent.
That's not, so it's not the actual distance.
No, it's not that. It's equivalent to this. Yeah.
But if you change variables, the
It's
square root, does that give you ellipticity in the image?
Yeah, it gives you ellipticity and it makes the grid look bad. Yeah. So one of the things that we want to do is to solve the parabolic problem with initial data that is just continuous, not Holder continuous. And for example, for the heat equation, even if you start with just continuous data, the solution becomes smooth. Is it the case for this operator also? And the answer is yes, that the solutions become smooth. And one way to prove that is by improving the estimates that we have on the regularity of solutions. So remember that in that estimate, we are controlling the higher order regularity of the solution in terms of the Holder norm of the initial data. Now we want to replace that Holder norm by a sup norm because with a continuous function, you only have a control on the sup. So we prove this interior estimate. So look at these cylinders. These cylinders are centered at a boundary point because this is where it's interesting to study the regularity. The interior is trivial. We have two cylinders which are bounded away from zero, and the red one is inside of the blue one. And this estimate says that the higher order Holder continuity of the function on the interior cylinder is bounded in terms of the sup norm of the solution on the larger cylinder. So we have a control on the regularity of the solution only in terms of the sup norm of the solution. But then we also have a maximum principle that I was mentioning, and by that maximum principle, the sup norm of U can be controlled in terms of the sup norm of the initial data. And that is enough to get smoothness of solutions. But before proving this Schauder estimate, we thought that one way to get this smoothness at positive times would be to prove a Harnack inequality. So that brings us to the Harnack inequality. So let's consider again the same parabolic problem and that we have a non-negative solution. The Harnack inequality says the following. In this picture, we have two cylinders and they are distant in time. They do not intersect. We have a lower and an upper cylinder. If we take the supremum of the solution on the lower cylinder, that's less or equal than a universal constant we take, that's the infimum of the solution on the upper cylinder. So this is a statement about how the solution to that parabolic equation decay in time. They cannot decay too fast because the infimum has to stay above the sup at an earlier time. And the proof of this Harnack inequality uses a stochastic representation. Think about that stochastic representation, something of the form that I showed before, a solution to a parabolic problem written as an expectation, as an average over some process. And that stochastic representation generalizes, so it's proved under hypotheses which are more general than the way stochastic representation are usually proved in the literature. And I will say a bit more about that. So now I want to say how do we get the Harnack inequality and why it is not obvious to do that. And I want to start with potential applications, because I said before that the reason why we started thinking about Harnack is because it was supposed to help us to prove smoothness of solutions when we only start with continuous data. So that is one potential application. Usually, so there are examples in the literature where when you have a Harnack inequality, you can get Holder's continuity of the data, and then once you have a little bit of more regularity, you can bootstrap that to get smoothness. Another application which we are planning to use it is to obtain upper and lower bounds on the transition probabilities. Something that looks so upper and lower bounds that makes the transition probability look like a hit kernel. Only in the hit kernel we have the Euclidean distance, now we have this new distance function. In the hit kernel we also have implicitly a measure, the Lebesgue measure. You will see that here the measure that is suitable for this operator is going to be a different measure, and it will show up in the following slides. Also, Harnack inequality can be used to study nonlinear problems. For example, when you study obstacle problems, it is very useful to have a Harnack inequality to get optimal regularity of solutions, or to study the free boundary. So it's just a useful technical result for a variety of problems. And now, possible ways to prove that. If we go back and we look at the Harnack inequality for harmonic functions, we will see that that proof uses the fact that we have a representation of the harmonic function using the Poisson kernel. So if you know things about the Fourier's function or about the fundamental solution, you can use those kind of things like lower and upper estimates to get the Harnack inequality. But we don't have that. So we are not going to take that approach to proving the Harnack inequality. Another way to do it is to apply Moser iterations. That applies very well to operators in divergence form, or to self-adjoint operators. And as I said, this operator is not self-adjoint. But, of course, there are generalizations to non-divergence form operators. And those generalizations...
So you think of the Laplacian as the divergence of the gradient?
Yes, exactly. Yeah.
Are you saying that it's not self-adjoint? It's not even symmetric?
It's not symmetric. Exactly, it's not symmetric. Yeah. But even if you don't have symmetry, there are generalizations. And Charles Epstein and Rick Matzel managed to adapt the Moser iterations to get the same Harnack inequality. Yeah. But we did it kind of at the same time, so we have this alternative way of proving the Harnack inequality using our probabilistic approach. And I think that it's not just an alternative way, but as I said, that our proof also establishes a stochastic representation, which is important for a variety of reasons. So I will come to that a little bit later. And there is also another method to do Krylov and Safonov to prove the Harnack inequality that works for operators that are not in divergence form. But of course that method also uses some kind of estimates, some LT estimates, which are not obvious how to derive for this problem that we have. And the method that we use is described by Stock, so it is due to Stock. And the idea is the following. So we have an operator L for which we want to prove Harnack inequality. Let's assume that maybe if we perturb that operator to an L hat, this operator L hat is much nicer, and we can prove the Harnack inequality for L hat. Then he has a way to show that you can get also the Harnack inequality for L, provided that the solution satisfies a stochastic representation. Because that method of proof uses exactly the stochastic representation and how they are perturbed one of the other. So for us, it will be difficult to get this stochastic representation. That's how we get to this type of result. And I have to say, what is this operator L hat? How should we choose L hat? This is from the work of Charles Epstein and Rick Matzel. So we want to choose it in divergence form so that we can easily or relatively easily apply Moser iterations. And the operator L hat is going to be equal to L, and it will have a lower order perturbation. So here we only have first order derivative in x and in y's. But when we look at the coefficients, they have logarithmic singularities. So we have here xi, ln, xj, and in the derivative in y, we have ln xj. So this operator looks less good than the operator L itself, but it does have the property that it is in divergence form. So we can find a bilinear form Q, such that when we take the inner product, here U and V imaginary line functions. So L hat U multiply against V, multiply against a wave function mu, integrate over the whole space, do integration by parts, and get a bilinear form. Roughly speaking, that bilinear form looks like this. So we have the first order derivatives in x, and we multiply them by the degeneracy. We have to keep it somehow in our model. And there is no degeneracy in the y variable, so it's just the derivatives in y. And then we have this measure mu. This measure mu is where we put the mutation rates. And you see it's a power-like measure. It's xi raised to the mutation rate minus 1. This measure mu has a probabilistic interpretation. It's a speed measure for the process, I should say here for the one-dimensional process. And the speed measure is used, for example, to compute the time that the process spends in a certain step. So it has a probabilistic interpretation. It's the same measure that an analyst would use to write an ODE, a second order ODE in divergence form when we do the Sturm-Liouville theory. It's the same kind of measure, only here it's a generalization to multi-dimensions. Also, so from this slide, it looks like this L hat of U is chosen a little bit artificially just so that we get something that it is in divergence form. Now, for the operator L, if we try to find the adjunct of L, the structure with respect to this weighted L2 space, the structure of L will be the same. So it will have these logarithmic singularities. So even from that point of view, it makes sense to be able to understand this operator L. So in our case, we have this L hat. This is a perturbation of L, and it is in divergence form, so we can get the Harnack inequality. And for what kind of solutions are we getting the Harnack inequality? So this slide is supposed to explain the solutions for which the Harnack inequality holds. And again, we have a parabolic problem, but now is defined for this operator L hat, not for L. And instead of writing the parabolic problem on the whole space SMN, the way we did it for L, we are going to write it in the neighborhood of a boundary point because we need to localize our results, because the Harnack inequality is a local result. So it's just enough to look at this picture. Omega, think about the omega as a neighborhood of this boundary point. So we will solve the parabolic problem on this neighborhood omega. Now, this omega will have two parts of the boundary. This blue part of the boundary, which coincides with the boundary of SNM, where we impose no boundary data. And it also has an interior part of the boundary, the red part, where the operator is not degenerate. So it is not possible to solve uniquely, to find uniquely a solution to this parabolic problem without a boundary condition on the red part of the boundary. And then we impose zero derivative boundary data. And because this operator L, it is in divergence form, it is easy to get solutions which are in a weighted Sobolev space. We do it the same as if it would be the Laplace operator, only we have to change a little bit the spaces. So for the Laplace operator, using the divergence structure, it is easy to get H1 regularity of solutions. So first order derivative in space, that it is L2 integrable. Now here also we will have first order derivatives in space of these functions u, which are L2 integrable in a weighted space. But it is more difficult to get regularity of the second order derivatives. That you have to work harder. Usually we do maybe a finite difference argument. It is harder to do it at the boundary, to account for the degeneracies and also for the logarithmic drifts. So for this kind of solution, we want to get a stochastic representation, and this is the stochastic representation. These solutions U, we can derive as the expectation of the initial data F applied to a
P is for pop up there.
yeah. yeah. Applied to a process Z hat. And then I will say in the following slide what this process Z hat is. But it's the process that is adapted to this operator L hat. And we have an indicator function here that just says that this process, we are going to stop it when we hit the boundary of the domain, the red part of the boundary, where we impose zero directly data. So this is the stochastic representation that once we have, we can feed it into Stuhl's method to get the Harnack inequality. So this process Z hat is a solution to
So can you show me what, I get to read what Z was?
Yes, Z hat is the unique weak solution to a singular Kimura equation. And now I'm going to show the singular Kimura stochastic differential equation. So the Z hat process, again, will have coordinates x hat and y hat. They are more complicated than the process XOT that I wrote at the beginning. It's driven by a multidimensional Brownian motion. But the reason why solving the stochastic differential equation is not obvious is for two reasons. One, that we have the square root of x hat I, so that makes this coefficient not Lipschitz. And we have a nice theory, just like for the ODEs, for the SDs that have Lipschitz coefficients. These are not Lipschitz. Also, we want the drift coefficient to be bounded. But our drift coefficient has logarithmic singularities, here and here. Despite of this, there exists a unique weak solution. And that unique weak solution, we use it to construct the stochastic representation.
The first one is not. It is bounded. The first red one is bounded.
The first one, well, you see here, we have xi and log of xj.
Oh, xj.
Is j, yeah. So it would be one-dimensional, it would be bounded. Yeah, but if it is multidimensional, it's not. Yeah. And I just want to compare the stochastic representation with previous results, with standard results in the literature. And I try to put the most general assumptions. So usually the diffusion matrix is assumed strictly elliptic. The drift coefficients are assumed.
Whereas yours are going to zero at the boundary?
Yes, yeah. The drift coefficient usually is assumed to be bounded, and the regularity is very small, just measurable. And the solutions U for which we are proving the stochastic representation are usually assumed to have the W2P regularity. So we have second derivatives in space, which are LP integrable. And P can be 2 or larger than the dimension over 2 plus 1. And so our diffusion matrix is not strictly elliptic. The drift coefficients are not bounded because of the logarithmic singularities. And most importantly, the solutions, they only have H1 regularity. So only first order derivative in space, which is L2 integrable in a weighted space. And if we hope, and we don't have LP theory, so to get something like W2P regularity, we don't have an empty theory constructed for this operator, and instead we do not always have to do that. So I think the most important contribution is just it's not so much in relaxing this degeneracy or unboundedness of the drift coefficient. It is in the regularity of the weak solutions. The thing that we cannot, it is enough to assume just H1 regularity. And that is unusual because all of these proofs, they use Ito's rule, which is the chain rule in stochastic analysis. And when you do that rule, so when you take a function and compose it with the process, and you try to take the derivative of this process to see the variation, and you try to do a Taylor expansion, what you find is that you have to stop only after the second order derivative, because these processes have finite and non-zero quadratic variation. So the second order derivative is very important in seeing what is the variation of the process. But we don't have that. So it's like we don't know things about a very important term when we are doing some approximation. And our method of proof is completely different. We don't apply Ito's lemma. We use what we know about the transition probabilities. Yeah, and I won't describe that, but the first time to talk about this for anyone who's interested. And I'm going to stop here. So thank you very much.
Any further questions?
Why does having a stochastic representation help do a Harnack inequality? Can you explain that in some classical example, like harmonic functions on the disk or something like that? So, I mean, can you just, like take it?
So if I have something like this, a harmonic function on the disk, on D1, and I have some data F on the boundary of D1, then so we can represent stochastically this function. So U of X, we can write it as the expectation of F. And then we take the Brownian motion and we evaluate it at the stopping time tau. And this tau is the first time when the Brownian motion hits the boundary of the disk. So we have like this. We start the process somewhere inside of the disk, and this process will have different paths. We wait until those paths hit the boundary of the domain. We evaluate the Brownian motion when it hits the boundary, and we plug it into the boundary data.
What is W?
W is the Brownian motion.
Okay.
So W is this process. Yeah. Now what Strum does, and the distribution on the boundary is exactly that Poisson kernel. What Strum does, it says, okay, I have the Laplacian, and then I'm adding a drift, a lower order perturbation. I set it equal to 0, again on B1. And then we have, again, let's take the boundary data F.
What's B?
B.
Little b.
Is B?
Little b.
Oh, little b, it's a drift. It's a vector field.
Just some bit.
Yeah. So I'm just adding a lower order perturbation to the operator.
Wait, did you prove the Harnack inequality in the first case already?
No, but we know it's true in the interior.
Okay.
Yeah. But what I want to explain a little bit from Sturm's method. So these solutions will also have a stochastic representation that looks just like this one, but the process that goes in there is a different process. Now, if I can use actually the same process, but I need to do a modification. So if I use the same process, the same Brownian motion, then I have to weight it by, this is the marking gate, so that's why I write it M tau. This is a marking gate. So you see that the way, maybe I should put here a hat. just to show that these are solutions to another equation. So
is it obvious how B determines N?
Yeah. It's a theorem, Gibson's theorem. So this NLP it's an exponential of the integral 0 to t b of ws dws minus 1/2 the integral 0 t then the norm of dws squared ds. So this is like a change of measure. I'm omitting some things. And who tells me that I can do this? It's what before the Gibson theorem. And so this is the martingale. If this B is bounded, it's very easy to show that something like this is the martingale. For us, this B has those logarithmic terms, so it's not bounded. And it's not obvious how to show that this is a martingale, but it is possible to do that. And this is Stump's observation somehow. He knows that the way these two solutions can be represented stochastically, it's almost in the same way, only I have to add a correction term in the stochastic representation. And he's using that correction term to get a Harnack inequality for L, if you know it, for L hat, or the other way around.
So you're saying if you don't think probabilistically, Dennis is going to get mad at me, but if you don't think probabilistically, then there's a modification of the Poisson kernel, and you can estimate it in the same way as you do Poisson kernel to get Harnack inequality?
Yes, yeah. But for example, so as you say, a modification of the Poisson kernel is given by this martingale. But it's very difficult to see what the modification is, even if you know this martingale.
But you just need to know the singular structure, right? If you want to get bounds.
Yeah, exactly, yeah. So that's, for example, a question that we think about. How can you get bounds, for example, for a Poisson kernel, if you know that the two Poisson kernels are related through such a martingale? And so when you look at this martingale, the problem with it is that it is path dependent. You see, I have to look at the values of this process from time 0 to time t, and that path dependentness is difficult to work with.
Any other questions? So we will go for dinner at 7 o'clock to tavern. So people who are interested, just let me know after the talk. And I thank Camelia.